In this lecture, we're going to look at rate determining step and the Arrhenius equation, which is kind of an extension of the rate equation. So you must have watched that lecture before you attempt this one. What we need to be able to do is explain the term's reaction mechanism and know what we mean by the rate determining step. We need to be able to propose the steps in a reaction mechanism from the rate equation and also the balanced equation for the overall reaction. And then we'll move on to our Arrhenius equation. So we're looking at describing the effect of temperature on the rate constant K and how we can use the Arrhenius equation to calculate activation energy. So let's start with the mechanisms and rate determining step bits. Firstly, to explain what we mean by rate determining step, it's handy to think about your own journey to work or school. So quite often, you might have a small walk to a bus stop. Maybe it's at the end of your drive, so that's quite quick. You then might have your 5-mile bus journey, so that's quite a long bus journey that will take quite a while, particularly because the bus will stop all the time. And then once you've got to your bus stop, you'll get off the bus and may only have a very short walk from the bus stop to the school door or your work door. So if we look at the 3 sections of your journey to work, of the 3, this one is going to be one that takes the longest. This is going to be the one that ultimately will decide how long your journey is. Any delay in the other 2 steps will only be very, very small. So the 5-mile bus journey is the part of your journey that determines really how long your journey takes. We can relate that to reactions in chemistry. So firstly, there are some reactions that will literally just go from the reactants to the products in one step. They just all react together. That's an example here. So we've got A plus 2B going to D. Now, if that was all happening just in one step from start to end, you would expect the rate to depend on A and 2 lots of B. So the rate equation would look like this. You'd have A and B squared because you need 2 lots of B and only 1 lot of A. So that rate equation suggests that that reaction literally goes from start to finish in one step. Alternatively, a reaction could take place in multiple steps. So rather than just going from the reactants to the product in one step, it could take place in a series of steps, a bit like your journey to work. That could happen with this reaction. If we look at an alternative rate equation, the rate equation could be just including B squared. So this tells us that the rate depends on 2 lots of B. And that would suggest that whichever the slowest step is in this multi-step mechanism includes 2 lots of B. So the 2 steps might be 2 lots of B becoming C, and then C combining with the A to make D. In this case, the first step there is very, very slow. It is that step that's like your equivalent to the bus journey. That is the one that's taking the time and really is the one that's dictating the rate. The second step happens as soon as C is made. So it's step 1 that is slowing everything down. So step 1 is the rate determining step. C is what we would call intermediate. It's made and then used up again. So it does not appear in the overall equation because you make it and then use it up. So overall, you've just got 2 lots of B and 1 lot of A becoming D. So we call C the intermediate. Let's look at another example. So we've got A plus 2B going to C plus D. The rate equation only includes 1 A and 1 lot of B. So that tells you that the other lot of B cannot be involved in the rate determining step. So a possible first step is A combining with 1 lot of B to make P, and then P further reacts with the remaining lot of B to give C plus D. And you can see that in the rate equation, we've got 1 lot of A and 1 lot of B, and that would suggest that it is that first step that is very slow and is therefore the rate determining step. So it's that first step that's slowing everything down. As soon as P forms, it very quickly reacts with B to give C plus D. So step 2 is not slowing everything down, it's step 1. And again, in this case, P is an intermediate. It's made and then used up. Okay, let's have a quick question then. So have a look at this. I want to know which is the rate determining step 1 or step 2? And then also what is the intermediate in this reaction? Okay, so if we look at the rate equation, we've only got 1 lot of M2 in the rate equation, and that must mean the rate determining step is step 1. And M is the species that is made in step 1 and then used up again in step 2, so M is the intermediate. In terms of the rate equation, if step 2 was a rate determining step, you would expect to see N in the rate equation, and it's not there. So that's how we knew that it had to be step 1. Let's have a look at some of the more tricky aspects of this. So we've got the equation A plus 2B going to the products D and E, and we're given a rate equation of K, A and H plus. Now the thing to note here is H plus is in the rate equation, but it's not in the overall equation. And that must mean that H plus must be involved somewhere, but it doesn't change overall. Because if it did change, it would be in the equation. So this must suggest that H plus is a catalyst. It's there at the start, it remains unchanged at the end, but it speeds up the reaction. So it could feature in the rate equation because it's speeding up the rate, so it is affecting the rate, but it's not in the overall equation because overall it remains unchanged. So we have a look at possibilities for this. Step 1 would be A combining with H plus to make AH plus. That AH plus is an intermediate and is used up in step 2, where it reacts with B to become AB and H plus. So your H plus is regenerated there in step 2. And then in step 3, the AB from step 2, which is also an intermediate, combines with the second mole of B to form the final product D and E. And since the rate equation does not involve any B, 2 and 3 cannot be the rate determining steps. So step 1 must be the rate determining step and H plus the catalyst. Finally, here's another example. So we've got A plus 2B again, giving D plus E, but this time the rate equation is K, A, B squared. So we've got 2 steps again in this mechanism. So 2B becoming B2, so just 2 molecules of B or moles of B combined to make B2, and then the B2 intermediate reacts with the A to get D plus E. Now there is A in that rate equation, and that means that the step 1 cannot be the rate determining step because there's no A in there. Step 2 must be the rate determining step. The reason for this is B2 came from 2 lots of B. So in the rate equation, we don't include intermediates, but we can include what those intermediates came from. So B2 is in the rate determining step, but it came from 2B. So in the rate equation, we have B squared and then the A. So this step 2 is the rate determining step in this case. Let's have a look at applying some of this then. So on the screen now, you've got a 2-step mechanism for nucleophilic substitution. Now you're used to nucleophilic substitution just being the nucleophile attacking and the halide leaving all at the same time. This is an alternative. So in the alternative, in step 1, the chloride leaves and forms a carbocation. And then in step 2, that carbocation is then attacked by the nucleophile. So just an alternative mechanism for nucleophilic substitution. And we can use the rate equation to determine which of these 2 steps is the rate determining step. So pause the slides while you use the data on this screen to work out the answer to A, B, C and D. Okay, so firstly the rate equation. Let's have a look at the nucleophile impact first. So from the top experiment to the middle experiment, the nucleophile concentration is increasing and the haloalkane is staying the same. The initial rate is also staying the same. So when the nucleophile concentration increases, the initial rate does not change, which suggests that the nucleophile is 0 order in this reaction. We then look at the bottom 2 experiments to figure out the haloalkane. We can ignore the nucleophile because we now know that it's 0 order. The haloalkane concentration doubles, as does the rate. That must mean that the reaction is first order with respect to the haloalkane. So the rate equation will look like this. We can then just plug in any sets of data from any of those experiments, line 1, line 2 or line 3, into that equation to figure out the rate constant, and the units are just going to be seconds to the -1. So now we know the rate equation, we can use that to determine which is the rate determining step. So the rate determining step only includes the haloalkane, and therefore it must be step 1. If step 2 was a rate determining step, you would expect to see the nucleophile in the rate equation as well. So the rate equation, if step 2 was a rate determining step, would be the nucleophile and the haloalkane. Again, pause the slides whilst you have a go at deducing the overall equation for this reaction and then the rate determining step. If you're not sure how to deduce the overall equation, you need to cancel anything that is made and then used up, so any intermediates, and anything that is there at the start and there at the end. Okay, so firstly, the overall equation. Well, we can see that NO2, one molecule is there at the start and one molecule is there at the end. So we can cancel one from the start and one from the end. We can also see that the NO3 is an intermediate. It's made and then used up. And that leaves us with, on the left-hand side, an NO2 and a CO, and on the right-hand side, an NO and a CO2. So that is the overall equation. The rate equation suggests that the rate depends on NO2 squared. Well, there are two NO2s in step 1. So step 1 is a rate determining step. If step 2 was a rate determining step, you would expect to see CO in the rate equation as well, and it's not there. So step 2 could not be the rate determining step. One final question then, pause whilst you have a go at this one. So if you work through and see what's there at the start and there at the end and what's made and then used up again, you will be left with one molecule of propanone reacting with a molecule of iodine in acidic conditions to form the ICH2COCH3 plus HI, or they've written it as H plus and I minus. Determining the rate determining step, well, the rate equation shows you that H plus and the propanone are involved in the rate determining step, so that suggests that the rate determining step is step 1. We're now going to move on to look at the effect of temperature on the rate constant K and the use of the Arrhenius equation to calculate activation energy. Okay, so let's have a look at the Arrhenius equation. So it links the rate constant K to temperature and activation energy. So it's shown here, we've got K, which is the rate constant, and we know the units of the rate constant can vary. We've then got A, which is the Arrhenius constant, and the units of the Arrhenius constant are the same as K for each reaction. So again, they change, but they match K in every case. We've then got the activation energy, and that is in joules for this. So that is in joules per mole. We've then got R, which is the ideal gas constant, and we've got temperature, which must be in Kelvin for the Arrhenius equation. The E there, so in this case, we're going to use natural logs. So E is the inverse of natural log. For all intents and purposes for us, we're just going to use the buttons on the calculators to use natural logs and the E function. Now, the Arrhenius equation is often used in logarithmic form. If you're uncomfortable switching between the two forms of this equation, I suggest you learn them both the normal form on the left and the logarithmic version that we're going to look at now. So in order to convert from the equation we've got on the left there to the logarithmic form, we need to take logs of both sides. And that will give us ln k, so ln is just natural log of k, equals natural log ln of A minus EA over RT. So because E is the inverse of the log or the natural log, when we you do take lns of each side, that E goes and it just becomes minus EA over RT. As I say, if you're not convinced about how to do this, learn those two forms of that equation, and you're also going to need to be comfortable rearranging them. Now, there's two ways that these equations can be used: numerically, which we usually use the version on the left, and graphically, which is where we usually use the version on the right. So here's a numerical example. You're just going to be doing some subbing in to the normal Arrhenius equation here. So pause and have a go if you're confident. If you do get stuck, let the slides move on a little bit, and I've got a few hints for you. So you're going to be using this version of the Arrhenius equation, and the first thing you need to do is rearrange this to isolate the activation energy, and then you can just sub in. Again, if you're still getting stuck, allow the slides to move on a little bit, and there are some more hints. So starting with this equation here, in order to rearrange to isolate EA, we're first of all going to move the minus EA over RT to the left-hand side. So if it's minus on the right, we are adding it on the left. So we get this equation here. We're then going to move the ln k. So if it's plus on the left-hand side, we're going to take it away on the right. So we get that equation at the bottom there. And then we need to move the RT over to the right-hand side. So we're dividing by RT on the left. So we need to times ln A minus ln K, all of that, by RT to move it over. So we'll come up with this rearranged version here, and you can then sub in the numbers. So here's our rearranged equation. We're going to sub in the numbers. So we first of all need to use a calculator to do the ln of A and the ln of K. And we should get 31.5 and minus 8.91. Then we also need to times R, 8.31, by the temperature in Kelvin, which is 308, which gives us 2559.48. And then we're going to multiply all that together, and we get 103,428.59 joules per mole. We must remember that the Arrhenius equation, the activation energy goes in joules, so it will also come out in joules. And we can convert that into kilojoules, so it'll be 103 kilojoules per mole activation energy. In order to see how we use this graphically to determine the activation energy, we've got the Arrhenius equation there on the slide. We've got the log version there. We're going to have to rearrange this to see how we can plot it as a graph. So the first thing is, I'm just going to switch around the right-hand side. So instead of ln A minus EA over RT, I've got minus EA over RT plus ln A. I'm going to break the minus EA over RT up into two parts. So I'm going to have minus EA over R times by 1 over T and plus ln A. And you may be able to start seeing how this is going to become a line equation. So for a line equation, we need y equals mx plus c. So y will be, in this case, ln of k. M will be minus EA over R. X will be 1 over T, T being the temperature. And then C will be ln A. So for a graph, on the y-axis, we would plot ln K. On the x-axis, we would plot 1 over T, and that would mean that the y-intercept C would be ln of A, and the gradient would give you minus EA over R. So this is an example of a plot. So we've got 1 over T on the bottom, we've got ln K on the y-axis, and the slope or gradient of that line, and it should be a straight line, will give you minus EA over R. So if you work out the gradient and times it by R, you will get minus the activation energy, so you just swap the sign. Just remember, you can never have a negative activation energy. Activation energies are always going to be positive. If it comes out negative, you've gone wrong somewhere. So you should now be able to explain the terms reaction mechanism and the rate determining step. You should be able to propose the steps in a reaction mechanism from the rate equation and the balanced equation for the overall reaction. And you should be able to describe the effect of temperature on K and use the Arrhenius equation to calculate activation energy.